Hi friends, welcome to follow up. Let's have a look at problem 1091 again, shortest path in a binary matrix. In this video, we are going to explain a solution based on a variant of the famous Dijkstra's algorithm. So in the previous video, we explained a solution to this problem by using breadth-first search-based traversal. So here we explain the Dijkstra algorithm-based solution. So here we are given an n by n binary matrix called grid. So here I have changed it to capital A just for convenience of typing. So we want to find the length of the shortest clear path in the matrix. So if there's no such path, so we're going to return -1. So a clear path is here is a path from top left to bottom right. So with all the cells being value 0, and here all the adjacent cells of the path are 8 directionally connected, right? So the length of a clear path is the number of visited cells of this path. So let's recall the 3 examples. So example 3 provides us a edge case. So here the start cell has a value 1, so we are going to return -1. And in the first 2 examples, the outputs are 2 and 4 respectively. So here one thing we want to mention is that, so for example in example 1, so we move from 0, 0 to 1, 1 directly. So this is still regarded as 2 neighbors, or neighboring to each other, due to the 8 directionally connected assumption. So with that said, basically we are ready to do the coding. So we are going to first implement a solution or method here is basically Dijkstra's algorithm or its variant. So in the literature it's called A* algorithm. So basically you can check this Wikipedia page for more information. So here there are 3 main ingredients. The one is a heap structure, and the other is a distance map, right? And also we are going to, the main thing is the relaxation. So we are going to explain these 3 parts. So different from Dijkstra's algorithm, so typically we have a very specific measure for doing the heap. So here we need a heuristic function. So we are going to explain it. So with that said, let's look at the coding part. So for explicitly, so let me first let's see. I'm going to use a Cartesian products. So we're going to use product. So or you can do the things like we did in the previous video using the 2 for loops for generating the neighborings. So also I'm going to use heap, and also I'm going to use the from collections import, so default dictionary. So it's just for some convenience. So now let's look at code. First, I'm going to treat the edge case or edge cases, which corresponds to example 3. So if a not is 0, is not 0, right? So in this case, we are going to return -1 because there's no clear path for sure. Next, we want to design the variant of Dijkstra's algorithm for this specific problem. So first, I'm going to define the heuristic function. So here I'm going to call it h heuristic, right? So given a position, so we are going to return max h minus x, h minus y. So here the understanding might be like this. So if we use these steps to arrive at a position, let's see x and y, let's see x and x y, y, and then the heuristic will change to so starting from this point x and y to arrive at the bottom right. So the heap value for doing the heap sim will be d plus h xx or yy. So also it can understand this maybe just as a digest. So if you are at the very beginning at position in the bottom right, in other words n minus 1 and n minus 1. So here not h is n. So where n would be the let's see, make it right here. N is the length of a, right? So if initially we are at n minus 1, n minus 1, right? So the path length should be 1, right? So you can check h n minus 1, n minus 1 is 1. So this is the inconsistency. So with that done, so we need to do two things. First is the direction. So we want to generate the direction or the neighboring. So the direction. So we can use the product. So here we use 0, negative 1, 1, and 0, negative 1, and 1. So this gives us a list of each sort of a iterator of non-elements. Let's make it a list. So the first one will be corresponding to 0, 0. So now we just need the last edge, because an increment in direction 0, 0 actually is the cell itself, right? So this is one thing. Now let's look at the heap. So here I'm going to use we can use tuple, or we can use list. So h naught naught and 0, 0. So the first one is the heuristic function value, and the second two are corresponding to the position. So initially we are at top left, right? That is 0, 0. So also we need to first we need to heapify it. This to make it a heap, and then what we are going to do. So this is the direction and the heap. Let me write here the heap, and also we need to map to track the distance. So distance map. So here let me call it dmap. So I'm going to use the default dictionary, and I'm going to set, if originally a position, we're going to set its value to be infinity. So now also this initialization, let's say 0, 0, and this position we're going to set it to be 1, right? So one cell. This is two of the three ingredients. One is heap, and one is the distance map. So next we are going to use a relaxation, right? So this will be a standard while loop. So here let me write relaxation step. So first let's get the position information. So here we have heap q, heap pop. So we're going to pop from this one, right? And then we get the distance. This is d xy. And then first let's check if we reach target. So if we reach target, this criterion is if x equals n minus 1 and y equals n minus 1. If this is the case, we are going to return d, right? This is what we need. So next is the specific relaxation step. So we check the neighbors, and we see if from the current position xy we have a better path to arrive at the neighbor. So basically for dx, dy in direction, right? So notice that direction now is a list containing 8 elements. And then we are going to move forward one step. Let's call it xx and yy. So it's x plus dx, y plus dy. So this is the new position, right? So now let's check first if this is outer bound. So this xx less than 0, or yy less than 0, or xx greater than or equal to n, or yy greater than or equal to n. So this means the neighbor xx and yy is out of bound, or so a xx and let's see axx and yy is not 0. So in this case it's not valid. right? So we are going to continue. This is just a sanity check, and then the specific relaxation. We check if from x and dx, from xy to xx and yy, we need one more step. So if d plus 1 is less than d map xx and yy, so you can put like this. This is a tuple, right? If you write like this, it's also interpreted as a tuple. That will be fine. So if this is the case, then we're going to update this xx, yy to be d plus 1. And then we also put the information into the heap. This heap q, heap push. So this heap, and then the information we're going to put is it's d plus h xx the yy, right? And then what we're going to include is the position, new position information, right? So that's basically the main logic here. So this step, basically this two line here, is the relaxation. So now if there's nothing has returned after we exit this while loop, so we're going to return -1. It means that we do not have a valid or clear path. So with that said, basically that's about it for a solution to this problem, the second one. Let's first do a test. No module heap, so here heap q. So now let's check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic cases very fast. So let me give a quick summary for this video. So in this video, we explained a variant of Dijkstra's algorithm for this shortest distance problem in the setting of binary matrix. So in the implementation, there are three main ingredients. One is a heap, and the second is a distance map, and the main step in the algorithm is the relaxation. So in this variant, we also should design a heuristic function to suit the needs here. So depends on the problem, maybe we need to vary the heuristic function. With that said, that's basically about it for this video. Thank you.